Hi everyone, my name is Mingshan Jia. I'm a PhD student at the University of Technology, Sydney. Welcome to my presentation on closure coefficient in complex directed networks. First, I will introduce some background knowledge about measuring clustering in networks. One classic measure is the clustering coefficient. It has become one of the standard measures to describe networks. It captures the degree to which the neighbors of a focal node connect to each other. Notice that here, the focal node serves as the central node in an open triad. An open triad is an unordered pair of edges sharing one node. The definition is here. The numerator is the number of triangles with node I, and the denominator is the number of open triads with I as the central node. For example, here, we have the number of triangle equals 2 and the number of open triads equals 6. Another measure of local edge clustering, the closure coefficient is recently proposed. By having the focal node as the end node in the open triad instead of the central node, it provides new perspective on network clustering. Specifically, it captures the degree to which the two hop neighbors of a focal node connect to the focal node itself. The definition is given here. So here the numerator is twice the number of triangles with node I, and the denominator is the number of open triads with I as the end node. The number of triangles is multiplied by 2 because a triangle can be constructed from 2 open triads with I as the end node. For example, in the same example, still we have 2 triangles, but this time 4 open triads with I as end node. Therefore, it is calculated by 2 multiplied by 2, then divided by 4. This new metric has proven to be a useful feature in network analysis. However, it is defined for undirected binary networks and cannot be applied to complex directed network. And in real-world situation, the relationships between components can be non-reciprocal, heterogeneous, and negative. So here we propose the directed closure coefficient in order to analyze in complex directed networks. So first we take direction into consideration. An edge can have one direction or 2 directions on it. We view bidirectional edge as 2 unidirectional edges here. So an open triad with 1 bidirectional edge is counted as 2 open triads with unidirectional edges, similar for directed triangles. Now let's look at the formal definition of the local directed closure coefficient. Compared to equation 2, the triangles and open triads are now directed, and the number of directed open triads is also multiplied by 2. This is because the closing edge of a directed open triad can take 2 directions. For example, in this graph, the number of directed triangles is 4, and the number of directed open triads with I as end node is 7. In order to measure at network level, we then propose the average directed closure coefficient. So this is the average of the directed closure coefficient over all nodes. We also have an example here. To further study, we classify 8 possible directed triangles into 2 groups according to the direction of the closing edge. In the first group, the closing edge is emanating from the focal node. In other words, the focal node serves as the source node of the closing edge. In the second group, the focal node is pointing to, the closing edge is pointing to the focal node. Put it differently, the focal node serves as the target node of the closing edge. Notice there is no such distinction when the focal node is the central node because the closing edge is not incident to the focal node. According to these 2 groups, we give the definition of the source and the target closure coefficient. Take the source closure coefficient as an example. The denominator is not different from earlier, but here the numerator is the number of source triangle of node I, which means that we only take into consideration the triangles where I serves as the source node of the closing edge. For example, in this directed triangle, we have 3 source triangles and 1 target triangle with node I. These two metrics evaluate the extent to which the focal node is acting as the source node or the target node of the closing edges in triangle formation. In the example below, we have the source closure coefficient equals to 0.5 and the target closure coefficient equals to 0.07. It implies that when a triangle is formed with node I is more likely to be the source node of the closing edge. So far, the study is focusing on binary networks. However, in many networks, we need a more accurate representation, such as the frequency of contacts in social networks and the traffic flow in road networks. That's why we are interested in extending it to weighted networks as well. So here it's the definition in weighted network and the weighted directed networks. Now let's quickly discuss the time complexity. It seems that in this equation it takes up to O(n) squared. Fortunately, in real-world networks, the adjacent matrix is very sparse. In actual implementation, we only need to obtain the neighborhood information of a node. Thus, the time complexity reduces to OK bar square. And this is the time complexity for the average directed closure coefficient. We conduct experiments on 12 directed networks from different areas. We can see that in all 12 networks, the average directed closure coefficient is less than the average directed clustering coefficient. In other words, fewer cliques are formed from the end node-based open trials compared to the number of cliques formed from central node-based open trials. The scatter plot show their relationship more clearly. The Pearson correlation is positive but weak. It shows that the directed closure coefficient provides complementary information to the classic clustering coefficient. And the second, similar networks exhibit similar relationships between them. Our next experiment is link prediction in directed networks. It is known that in undirected networks, the neighborhood-based methods, also called similarity-based methods, such as common neighbors at Mikadar, are simple and powerful. However, in directed networks, we predict not only the existence of a link, but also the direction on the link. Therefore, we choose the directed variations of the classic methods as the baselines, which has directed common neighbors directed at Mikadar. For example, here, the common neighbor index of node pair S and T is 4, and the directed common neighbor index for them is 2. Combining the idea of common neighbors as well as source and target closure coefficient defined earlier, we propose 2 indices to measure the directed similarity in networks. First one is the closure closeness index, CCI. It is contributed from 2 parts. One part is the directed common neighbors, and the other part is the sum of the source and the closure coefficient. As we have discussed earlier, the source and the target closure coefficient evaluates the extent to which the focal node is acting as a source node or as a target node of the closing edge. So a sum of them depicts the trend of forming a link from S to T in clique formation. The second proposed index is only a small change on the first part, which shows the common neighbor instead of the directed common neighbor. This is because the second part can already bring in the inclination. So here, we count all common neighbors of node S and T regardless of the direction. We skip over the setup. Table 2 gives the result. We see that CCI has recorded the highest precision in 5 networks, and eCCA has recorded the highest precision in 4 networks. It suggests that including the local structure information of closure coefficient leads to improvement. And sometimes the improvement is significant. In AddHealth and ePenning, eCCA is over 30% better than the baseline methods. And in other 6 networks, the proposed indices is over 5% higher than the baselines. So in conclusion, we propose the directed closure coefficient and the extension in weighted networks to measure edge clustering in complex directed networks. To study further, we also propose the source and the target closure coefficient and 2 similarity indices based on them. We anticipate that the directed closure coefficient can be used as a descriptive feature as well as in other network analysis tasks. And that's it for our for this presentation. Thank you very much.